Prabhat. Prabhat. Now it's audible. Am I audible?
Yes, sir.
So, okay, fine.
Good morning, everyone. This session will be taken by Professor Bidyadhar Subudhi sir on the topic Adaptive Control of Microgrid. Professor Bidyadhar Subudhi received a bachelor degree in Electrical Engineering from National Institute of Technology, Rourkela, Master of Technology in Control and Instrumentation from Indian Institute of Technology, Delhi, and PhD degree in Control System Engineering from University of Sheffield, UK. He took over the charge of director NIT Warangal on 27th April of 2023. Prior to this, he was a professor in the School of Electrical Science and Dean R&D at IIT Goa and is currently on deputation. He served as a professor, Electrical Engineering, Dean Alumni Relation and Resource Generation, HOD Electrical Engineering at NIT Rourkela. He also served as a visiting professor at University of Canada and in Asian Institute of Technology, Bangkok. He was a recipient of the prestigious Samanta Chandrasekhar Award of the Odisha Vigyan Academy, Government of Odisha, and Distinguished Alumnus Award, NIT Rourkela. He is a fellow of the Indian National Academy of Engineering, Asia Pacific Artificial Intelligence Association, IIT UK, and distinguished speaker for ACM. He serves as a technical committee member of the IEEE Technical Committee on Intelligent Control, IEEE Consumer Electronics, Power and Energy, IFAC Computational Intelligence in Control, Steering Committee member of the Asian Control Association, member of the IFAC Council, and Vice Chair of the IEEE Technical Committee on Consumer Electronics, Power and Energy. He serves as an editor with IEEE Transaction on Sustainable Energy, IEEE System Journal, IEEE Access, and IIT Electronics Letter. His research interests include system and control, control of power system, embedded system, and AI and machine learning. He has supervised 40 students, 40 PhD students, published 164 peer-reviewed journal papers, 110 papers in conference proceedings, 14 book chapters, and 8 books. Now I would like to invite Professor Bidyadhar Subudhi sir for his lecture. I hope you all have a productive day.
So, thank you very much. Thanks, Prabhat, Mona Lisa, Arnav, for organizing such a wonderful program for the benefit of the electrical fraternity. So, I would have been uh, there with you. I'm using this platform to share some of my experience. So, let me share my slides. Prabhat, Prabhat, need permission to share. Permission to share. Prabhat, now is it okay? Slide is visible? Prabhat?
Yes, the slide is visible, sir.
Okay. So let us start discussing. So today, good morning, dear participants. Today the topic what I have chosen to discuss with you is basically distributed adaptive control of microgrid. And I will first introduce the concept of the microgrid and its control problems. And one controller I will be presenting that we have designed, that is called adaptive backstepping controller, and some results and discussion. So all of us know that the traditional power system, am I audible?
Yes, sir. Audible, sir. Sir, audible,
Yeah,
sir.
yeah. So the traditional power system, as you know, that comprises of all these generation, transmission, distribution, encompassing all these fuels, fossil fuel based power or hydel power or nuclear power. But here the need arises to supplement the renewable for the obvious reasons, for reducing the carbon footprint and to raise our power demand, to meet our power demand. So therefore, we in the modern power system, we need to integrate the distributed generation, that is the different renewable energy sources, for example, the photovoltaics or wind energy conversion system. Many such renewable options can be added up with the conventional power system. As a matter of fact, we are able to supplement the power from renewables. Also, we want to build smart grids with all these communication and the other the sensors, computing, everything, and the servers, everything inbuilt. And then this distributed generation, after incorporating those in the power system, we have the benefit in one hand, that is, we are able to reduce the carbon footprint. We are able to get this power supply from the renewables. And but while doing so, of course, we are reducing the infrastructure in building a centralized power system. On the contrary, if you go for a distributed generation, you should have a localized power system in your place. So therefore, these are called distributed generating systems. For example, the photovoltaic, wind, or anything in that bracket. So the typical modern power system comprises the same like transformers. We have the power station and we have the consumers. But here the additional advantage is that we integrate the renewable and also we make our grid smarter in terms that a bidirectional kind of tariff. That means the cost consumers are no longer only consumers; they are the pro consumers. That means they produce their own electricity for, let us say, a small colony. You can install the photovoltaic power there and you have your power, so you can connect them as a microgrid and use the power from there. And when there is a surplus power, you can connect it to the integrated the grid and feed power to the grid, utility grid. And when there is no generation, at that moment you can take power from the utility grid. So your tariff will be both way. That means it is basically one way you are selling the power, the other way you are consuming the power. So the net metering, that means the tariff, the usage of power is very important. The another aspect is that by designing this, the power supply and demands requirement, we can have you can schedule the power requirement. For example, if it is a daytime usage, you can use more photovoltaic rather than wind or maybe other sources. So therefore, your economy goes up. So this is one of the benefit of integrating the. So basically, what we understand by a microgrid, it is basically a small power network that are exploited to supply local loads in small geographical regions. So by that, what happens? The infrastructure cost goes down and maintenance becomes easier, and you can operate them in the isolated as well as in the grid connected manner, as I discussed. So the main components of a microgrid are the distributed generating sources like the solar photovoltaic or wind energy converter system or geothermal, like many other options could be taken up. And we have a interconnector switch that connects the microgrid to the main grid or disconnect. So either your microgrid can operate in the isolated mode or a grid connected mode. So for that operation to achieve, we need a interconnector switch. And we have the storage devices because sometimes there is a question of instability. So there the kind of storage will provide the stability when there is a outage of power supply. So the grid management software. So it is basically that decides how to operate the grid, this microgrid and main grid, how to have that control so that the economic operation can be achieved. Of course, some controllable loads, for example, you can connect the electric vehicles and all controllable loads they are possible. And a robust communication network is necessary because, as I said, that you need many things. You need the security system, the cyber security. You need the how to prohibit the cyber attacks because the blackout is a major concern in power system. So if your microgrid connected to a main grid, there is a security issue or a cyber attack problem. So we need to have a secure communication network. And not only that, we need to connect all the components in the device. For example, you want to connect the converters to the control system, or your consumers may be communicated well how when to whether to sell the power to the grid or take the power from the grid. All these communications that can be accomplished, or any control or the maintenance or maybe what you call protection, everything can be accomplished. So then what is the benefit we get by using microgrid? So there is less burden on constructing a huge infrastructure on a centralized power system. Unlike a centralized power system, this microgrid that needs the renewable sources are the distributed power system. Integration of renewables and storage technologies. So we are facilitated with, we get the opportunity to connect several renewable sources to the microgrid. Also, we can ensure the power quality and reliability because of the distributed generation connect with the microgrid. And also, as I mentioned, the blackout. Because if everything is a centralized power station, so somewhere there is a mistake, the entire blackout, the power supply is very disastrous mode. So in that case, if it is a possible to have to avoid these blackouts by using the microgrid because they are localized supplies. So in summary, the microgrid comprises of several distributed generating sources like photovoltaics. We have different controllable generation also possible like fuel cell, and these we have the different controllable loads. We have same the utility grid is also there, and we connect all of them in the point of common coupling. And we could have the storage devices for the stability, and you could also connect some backup generator sets. So by this arrangement, we are able to achieve the flexibility in the power system. We can enhance the resiliency. That means before anything happens, the fault happens or blackout happens, we can, our microgrid manager will, our decision making logic will help us how best we can take the resiliency into consideration. And of course, there is low cost involved, as I mentioned, in the infrastructure and in the reduced transmission line because there is a local the distributed generation. And so when there is a energy crisis or blackout, we can still be able to get power because all the microgrids may not be having the same problem. So the summary is that all these microgrid facilitate integration of the renewable sources to the main grid. But while getting all these advantages, there are challenges here. So what are the challenges? The challenges here, how to synchronize all these participating digi sources and when there is communication constant, because any communication you talk about, there is always a communication delay. So when there is a communication delay, so it becomes difficult to take care of that delay in synchronizing all the DG that are connected to a microgrid. Similarly, as you know that any microgrid or a power system, we always use some kind of converters or inverters, the power tuning circuits, and they have the switching cycle. So the switching frequency or the switching mode of operation, also the switching function is a nonlinear function basically. Not only that, the other uncertainties like the dynamics, you cannot accurately model it. And there are disturbances in the grid or maybe load or somewhere. So therefore, in presence of all these uncertainties and disturbances, how to achieve the efficient operation of a microgrid, that is a challenge. So in presence of all these uncertainties and disturbances, how you would be able to get an accurate model? How to handle nonlinear loads, because nonlinear loads produce harmonics and that is a great concern. So how to avoid that so that you will be able to obey the grid codes, where the grid code says that your TSD, the total harmonic distortion, should be less than 5%. So that should be ensured. And how to switch on and switch off between the two modes of operating the grid or microgrid. That is, one is the islanded mode or the isolated mode, when you want to only operate microgrid, you do not connect them to the grid. And the other hand, when you want to connect in the utility grid with the microgrid, the synchronization, so there must be a seamless transfer. There should not be any difficulty on that. And also how to ensure the power quality in the microgrid, and also the time of convergence, when let us say in a microgrid there are 10 DG units like photovoltaic sources, etc., and their output voltages should be regulated with normal or nominal frequency and voltage of the point of at the point of common coupling. So how quickly this convergence can be achieved, and how to support plug and play operation. What is plug and play operation? Suppose in a microgrid there are five, let us say DG, that is PV or wind or whatever, distributed generating units, and one DG goes wrong or goes faulty. How best the other DG will take care of quickly so that the nominal frequency and voltage could be maintained. So this is called the plug and play operation. So there are many issues. The issue is with the issue with the sensor and actuator faults on certain inputs, the balancing of the state of charge, and we have the plug and play operation, time delay, cyber attack, and there could be packet loss when you send information in the network. The packet could be, the information could be lost, and there could be utility grid failure, and there is a problem with the bidirectional flow, like when you connect or a charge a electric vehicle, the not only the electric vehicle is being charged from the grid, but also from the grid to the vehicle. So there are a lot of challenges involved in case of both the input side control and the outside, of the microgrid. And also the intermediate stage also we have, and control side also there are some problems. So there are a lot of challenges here. So that I was mentioning. Either you can use the microgrid in autonomous mode or the islanded mode or a grid connected mode. So both the operations are possible. So in microgrid, so what basically, let me give you an overview of this. So if you talk about the microgrid, microgrid, the first of all that in summary, the microgrid is operated either a grid connected mode or an islanded mode or isolated or autonomous mode. The generation connected, the generating units, the DG units connected to microgrid could be the renewable sources, maybe PV, wind, biomass, fuel cell. There could be storage devices like for the grid stability, for short-term or long-term stability. We need to have banks. We need to have ultra capacitors and flywheels. We need to have interface or solid-state relays for the control. And we have either the controllers could be centralized or decentralized. Decentralized means individual control provided with individual communication and they control individually. Centralized means entire microgrid is controlled by a centralized controller. So when you use a centralized controller, so then if that controller fails or computer fails, so entire system is a single point, the is a failure. So therefore this is not reliable operation. So therefore there is a need to operate the microgrid in a decentralized control mode. And then the protection and the coordination, this is very important because we know the phasor measurement units are one of the great achievement in handling the protection, where the fault locations can be diagnosed very fast using the phasor, synchro phasor. And also how to ensure the power quality, what kind of active power filter, active either a sound active filter or a series active filter you can use to ensure that the harmonics are compensated, and how best the reliability can be ensured. And similarly, the data collection, the communication, real-time communication is very important, because we want to get the data in real time from the sensors, from the meters, and how to monitor the operation in real time, and how to go for a supervisor control based on this communication. And also the demand response is to be integrated to the microgrid operation. That means how the real-time pricing can be embedded here, and how the active loads are being controlled, and how to go for the load shedding, how to take care of that. So these are some of the aspects, the summary of operating a microgrid. Now, the control aspect of the microgrid, what are the control challenges here? Actually, as you know, when you say that in one hand, the renewable energy sources you connect to the microgrid is a great advantage. But on the contrary, the renewable sources are intermittent in nature. For example, the photovoltaic power, system integration. Photovoltaic, the solar insolation is not constant throughout. The solar insolation may be intermittent in nature. So therefore, there is no, stability is a great concern here. The other aspect is that in case of a the central power station, the droop control is easier, because the generators have large inertia. But in case of the microgrid, the DG units, they, for example, photovoltaic units, they don't have a generator, and therefore there is the grid inertia is very low here. And in terms of the low grid inertia, how to mimic a situation of the generator kind of characteristic here to apply the droop control. Droop control means you want to operate all the generators or the feeding power sources at nominal voltage and frequency, and how to coordinate all these distributed energy resources, DERs, how they should participate. When one fails, how the other takes care of. When there is a low demand, how much is depending upon their ratings, how much they will be contributing. And therefore, the control task before us is basically either both the frequency and voltage of each DG unit or DER must be regulated at nominal voltage and frequency, and also active and reactive power control of the DG units with the main grid, and to synchronize all the main grid with the microgrid, and to operate the grid in a very economical manner. And all these control are achieved a hierarchical control function. That means they have a hierarchy. They have different level of priority in control. So this priority is basically tertiary, the zeroth level, the control, and then you have the secondary control. We have the primary control. So primary control is the level 0, the control where the objective is to stabilize the frequency and voltage when there is a fault. After the fault is over, or landing is over, so how to stabilize the frequency and voltage of the microgrid, and how to mimic the behavior of a synchronous generator of high inertia, so that you can implement the active the PQ droop control. That means if you control the Q or the reactive power, you control the voltage. You control P, you can control the frequency. So how to achieve those? And in the secondary control, the second level control, level 1 is the primary, level 2 is the secondary control, where the objective is how to restore the frequency and voltage deviation that are caused during the primary control, and also how to provide the reference values, the nominal values for the primary control. Similarly, the highest level of control called tertiary control, where the objective is to how to manage the power flow between the microgrid and the main grid, so that the economic operation can be achieved. And for details, if you are interested, we have a paper called Comprehensive Review on Hierarchical Control of Microgrid System that has appeared in a paper IT Generation Transmission Distribution in 20. So the secondary control, as you know, the secondary control is basically how to regulate the DG or the distributed generating unit output at nominal values. For individual DG output should be operated at nominal values. For example, ith DG output VOI should be equal to the nominal voltage B norm. And similarly, to synchronize all the DG unit output frequencies at the nominal frequency. So this secondary control can be operated in either centralized control mode or a decentralized control mode. In a centralized control mode, what happens? There is a central computer that communicates through all the DG units. And therefore, what happens, as I mentioned just now, if that controller fails, the entire microgrid operation fails. But on the contrary, what is being done, a decentralized controller or a distributed controller where there is not a single central controller that communicates with the individual DG units. Rather, every DG unit is being connected with the individual controller. So therefore, communication can be established and control can be easier, and there is no single point failure because one DG fails, but the other DG are still working. So that is the advantage. So this is the difference between the centralized and decentralized distributed control or the distributed control, where left side one is the centralized controller. As you could see, there is only one centralized controller. And as a matter of fact, when that controller fails, then there is a single point failure. There is a reliability is less. But on the right side, if you see this figure, each DG unit is equipped with a secondary controller. So therefore, when there is a problem with this, let us say with DG1 controller, but still DG2 and rest of the controllers, DG units work. So therefore, this is a reliable mode of operation. And we control this by using a communication network inbuilt. So that communication we can use, for communicating the different DG units. So one such, so then as I mentioned earlier, that the microgrid control is challenging because there are different uncertainties, there are disturbances, and in order to handle those uncertainty and disturbances, so we need to have a adaptive controller. And here we design an adaptive controller by using backstepping technique, and also we use a state observer that is called extended state observer. So the controller that I'm presenting here is called extended state observer based adaptive backstepping controller. And this paper has been recently published in IEEE Transition on Smart Grid. So the name of the article is an extended state observer based adaptive backstepping controller for microgrid. Those of you are interested for details, you can refer to this paper. And what to do here, we model the microgrid so by individual, there are a lot of DG or distributed generating units connected to the microgrid. Let us say we model the ith DG here. So the ith DG model where each DG is equipped with its voltage controller and current controller, and the DG is represented by a renewable energy source and a converter. And we have the secondary controller here, all these sensors and actuators. And we have different, like we have the problems with this when DGI is connected to DGJ, and there is a secondary controller. So this is the utility grid, and this is the point of common coupling. So what happens here? The lot of difficulties are here. Like we have the cyber attack, you could have the noises, we could have the communication fault, we could have the sensor and actuator faults. So if we model it with a, let us say DG1 to DGN, and we have the communication delay, we have the cyber security, and we have the nominal voltages. So this is the model of a DG unit where this RFL, LFL, they represent the filter resistance and capacitances. And these RCI and LCI, they are basically the line impedances. And this VBI, the VBI, and the IFDC bus voltage, VOI is basically the filtered output voltage, and all these Q axis and D axis current and voltages, and omega ni the control input here. The frequency is controlled here. Now, what you do is we first develop its dynamics. What you do, we put this, fault at this psi, and this term represents the on-model dynamics, and this is called a BIOS fault, and this is the sensor fault. So this is the dynamics when we consider the fault, and when you consider the we added these additive noises to represent the noise in the or disturbances, and we also represent the communication delay, that is tau, and this is the disturbance. So the motivation here is that we want to design a controller, a dynamic gain controller, so that we take care of all these uncertainties. So here this is the model. So this is the control structure. That means we have four DG units. DG means the either photovoltaic units. So we have the connectors or the line impedances RC1, LC1, these bus voltages, output voltages, and here is the controller. Now, what is the control challenge here? The control objective here is that how to restore the nominal voltage and frequency of DG units in presence of uncertainties, disturbances, and communication time delay and load variation, and how to support the plug and play operation. Also, how to take care of the transition between the two operating modes. The utility is connected to the microgrid, that is the grid connected mode, or it is disconnected from the main grid. It is called the isolated or islanded mode. And how to prioritize to give supply to the critical load and ensure uninterrupted power supply. How to ensure the accurate power sharing among the DG units, and how to support when there are load also disconnected for the plug and play operation. How to take care of the unbalanced unbalanced load systems. So the control design involves, as I said, the model in the previous slide I have shown you the model. So this is the model of the microgrid for IH-DG. So we connected the PV unit, we have the converter and the disk-link capacitors, a filter, VSI and filter. We have these controllers, voltage controller and current controller and power controller. So this is our objective is to design only the secondary controller here. So the purpose here is to restore the output voltage of each DG by tracking the reference value or the nominal value in face of uncertainties and disturbances. And what are the challenges here? The challenges are here that these voltages, that is the VDC and the load current, D axis and Q axis are not known precisely. There are uncertainties in the PWM switching function of the VSI, and there could be disturbances in the local loads, and there could be fluctuation across the bus bar voltages in, that their load, the bus voltage fluctuation. So to design a control so that we achieve this restoration, that means all the DG output voltages and frequencies must be regulated at nominal values. So this is the microgrid system dynamics. This is the PV unit, that is the DG, and we have the disk-link capacitor, the inverter, and we have these. And these are the models. So basically, the PV array dynamics integrated with the converter with the VSI. So this is the dynamics, and the VSI dynamics into the LCL filter. So both are considered here. So then once you get it, we represent that in a nonlinear state equation where we put di a term for the disturbances and phi a term for the uncertainties. And the states are basically all these voltages, currents, and the switching angle and the reactive power. So there are 13 states we have chosen. And where PVI and MDI, MQI, these are basically the PWM functions. And these are the voltages, and this is the common frequency or nominal frequency. And this is the matrix that contains the system dynamics. And this is the K, the disturbance matrix and uncertain function. So this is the dynamics we represent with considering the disturbance and uncertainties. And this is the definition of the F function, the nonlinear function, a state equation function, where it is a 13 by 13 matrix. and we have uncertainty matrix and the disturbance matrix. So then we design a backstepping controller. In the backstepping controller, we need that we should have the information from the neighboring DG units, and we have here there is a ESO here. ESO means extended state observer. So we choose a ESO. What is the purpose of ESO? The ESO, the benefit of using a ESO is that it lumps up all these disturbances into one, the added state of the system. So that state we can estimate. The extended state observer estimates the three states, that is 1, 2, 3, x at xi2, xi3, x. So these states are basically the observer states. So they represent the uncertainties and the disturbances. So those are estimated. Once they are estimated by this ESO, which is a nonlinear estimator, so those states are embedded with the system states. And then we design a controller, and this is we use the backstepping control. The backstepping control is basically a Lyapunov based controller. At each, instead of the Lyapunov controller where the last step you only check the stability for the closed loop dynamics, here the backstepping controller at each step we want to ensure that the stability in the design process, you ensure the stability is ensured, that each control law is derived. So the control law we find out is UI as this one, where all these K are basically gains and all these hats, X hat. So they are the estimated states. Those are obtained or achieved by using the extended state observer. So by estimating those, we implement this controller, and this is the structure of our model or the DG model or the microgrid model, where we have four DG units and we have the bus voltages and the filter capacitance and resistances, inductances, and all these DG units are being connected with a communication network, and the communication is established by and represented by a communication network or a diagram. And then we choose these different DG unit parameters. So like DG1 and DG2, DG3, DG4, and these are the different parameters. Like we have the control gains, we have the active load, reactive load, and we have the frequency, and we have we have these filter capacitance, inductance, and we have the cutoff frequency of the filter. So once we implemented the same in MATLAB fast. Once we implemented, we observed from the first figure that these are the these four line colors, the yellow and the green, and then this color. So all the red, so all these colors refer to the voltage outputs of respective DG units. And you could see here that all of them are maintained at a nominal value of 415 volt. And here also we could see the frequency of all DG output are maintained at 50 hertz. And here similarly corresponding active and reactive curves, they are maintained, because if you change, you regulate these by droop control. If you regulate the reactive power, you get the frequency. You regulate the active power, you get the voltage control. Sorry, you reactive power for voltage control, and this one, reactive power is voltage and the active power is frequency. So you could see at t equal to 0.5 second, load 2 is disconnected. So when load 2 is disconnected and t equal to 1 second, load 2 is again reconnected and increased by 50%. So still the deviation or the transition at the output voltages and frequency are taken care of. Here you could see that how this controller is providing the plug and play operation. That means at t equal to 1.5 second, the DG4, one of the DG units, is plugged out or taken switched off. And so at 2 second again it is connected. So during those periods you see the variation in active power and reactive power, and correspondingly it takes little time to come to the nominal value of 415 volts and 50 hertz. So so that means the controller is able to provide the plug and play operation. Now we compare the performance of the proposed controller, the ESO based distributed controller, with respect to some other controller, distributed averaging controller, and some the microgrid centralized controller, we could see that the proposed controller, that is the red one, is giving a superior performance in terms of regulating the output voltage of a DG unit. One of the DG unit we considered at nominal values. Rest also same, but I'm not showing here. Similarly, voltages of the so this is the ESO based backstepping controller. So we are getting at 415 volt. And the frequency also we maintain like this at 50 hertz. And when it is plugged out or plugged in, the one of the DC units, still we are able to maintain at 50 hertz. When there is a transition, quickly it goes to the nominal value. We also evaluate the performance of this controller when there is a switching problem, network delay. So time delay or the switching delay, or what we call the communication latency, is a great difficulty to handle. So as you could see, all these DC units, they are reaching the nominal value of 415 volt, or maybe the voltage here, 415 volt. So the frequency again 50 hertz. So even there is a communication delay. So still these DC units are able to handle those. And here when there is a fault, line to ground fault or line to line fault. So even if there is a fault here, so it takes care of the fault and goes to the nominal value 50 hertz and 415 volt quickly. So here also you could see the voltages, current and frequency during the fault condition. So the controller is able to ensure to maintain the voltage at the individual DG units at nominal values. Now we also developed a experimental setup for verifying. This is the one I showed you, that the MATLAB and Simulink results. Now here I will show you that how we have verified the controller efficiency in real time. What we have done, we have taken these voltage sensor, and we have different DG units. So we have DG means the what you call, we represent them as the inverter based DG, and the DC source and then the inverter. They represent individual DG in place of the PV system. And we use the real-time controller using a polarity or micro lab box. And we have the VSI here for control. We have the auto transformer as the mimic the grid to control the point of common coupling where to connect to different DG units. We have different sensors here and the load. So this is the schematic diagram of these experiments, and we have used the RS445 as the communication link. And we have the filter circuit, VSI, the converter, PV simulator. So what we have used? We have used a PV simulator here. And this is basically the polarity where the controller is implemented, and is the sensors, all the information are given to this controller. So now what you get is, we get the real-time result here. So the first one you could see when the load decreased. So the load decreased, there is a decrease in the nominal voltage across the DG output. But when the load increased, so again, you see there is a fall in the voltage. So, and then there's a DG plugged out, DG plugged in. So no matter with a short transition, the nominal voltage is maintained. Similarly, you can say the another case, DG2 is plugged out and plugged in, and load is basically increased. How quickly these are maintained at the nominal value. So the 2 DG we put it here, the output. Similarly, we have also considered that at a different time we have plugged out and different time we increase or decrease the load. But we could see that the voltages and the frequencies across the DG1 and DG2 output are maintained at nominal values, that is 415 volt or maybe 50 hertz. These are scaled down figures because in real time we have scaled down it. So, but nevertheless, this represents 415 volt and this is 50 hertz. So that's what we are doing, and this is about the when there is a load variation. So how to take care of the load variation using the proposed controller. We could see the voltage, frequency, active, reactive power responses under load variation, the plug and play operation using this proposed control is achieved. So the conclusion is that by using this observer-based, the extended state observer-based backstepping controller in the microgrid, where there are 4 DG units, we implemented both in MATLAB Simulink. We also implemented the same using the real-time setup, and we achieve the microgrid control objective in presence of all these uncertainties and disturbances. And also when there is a load variation, when there is a the noise, or when there is a communication delay. And we also achieved, compared to other controllers, averaging controllers, that the proposed controller is more robust in handling the uncertainties and disturbances. And this controller provides regulation, synchronization of DG in presence of the dynamic perturbation, like when suddenly you change a load, suddenly you take out a DG unit, still the controller provides appropriate control action adaptively, and by estimating the uncertainties and disturbances online through the ESO, and providing us the desired performance. And this is the set of references. So these are some of the references used to prepare this work, or to go ahead with this work. So this is all about the adaptive controller that we designed in the lab and verified experimentally. So now I may ask the participant to interact, if I can discuss something with you. Hello.
Questions from audience?
Hello, am I audible?
Yes, you are audible.
Okay, sir. Like you have been talking about the secondary controller, and how it can be helpful in the seamless transition between the grid connected mode and the islanded mode, sir. How it will be helpful?
Yeah, it's a good question. Actually, the one I am saying is basically with a the controller remains the same, doesn't matter. So only when is a grid connected mode, that grid is basically the grid dynamics is the it considers a controllable load in the controller. So without much difficulty, you can consider the grid dynamics as a disturbance or uncertainty and then go ahead with. But the basic objective is the droop control here, because the droop control in connecting the microgrid with the utility grid, you have to take care of that. The nominal voltage, all the grid voltage only. But when you don't connect to grid, you have to set a common voltage at the point of common coupling. Is that clear?
So you mean to say that you have to set the frequency and the voltage at the point of connection, and after that, I mean,
Yes.
okay.
Yes.
Could you just elaborate a little bit on that? Not
Yeah.
that
So
clear.
let us say put it like this. Suppose the grid, the voltage is 415 volt and frequency 15 hertz. So you want to apply the droop control. That means you want to control the active power of the individual. There is a droop equation. There is a droop coefficient. So you want to vary this coefficient in a manner that individual DC output voltage should be brought to that, to be regulated at that nominal value. And individual DG output frequency must be regulated at the nominal frequency. Now, when they are connected, when the grid is connected, instead of point of common coupling, or only the standalone based microgrid, you should consider the grid voltage and grid frequency. That's the only difference.
Okay. Thank you, sir.
Yeah. Good morning, sir.
I have
Good
a
morning.
question, sir.
Yeah, please.
Sir, as you have connected different DC sources, so have
Yeah.
you done any economical analysis of like different sources? When one will be in action, another will be in standby mode, like that? Have you done any analysis?
No. Here, economic analysis is not a part of the study. Economic analysis, you see, we cannot, suppose you have, let us say, somewhere the photovoltaic is more. So then obviously they have to, that is the only option left. There are places where like South India, many places, Tiruchirappalli, like that. Those area is very good for wind energy conversion. So there is an option. There is no question of comparison. Okay. So the option you have to take, which source you have to use. So it may so happen in some cases, let us say there is a rainy day or a stormy day. So in that case, there is no photovoltaic, but there could be wind. So you have to choose those options.
Okay, sir. Thank you, sir.
Good morning, sir.
Good morning.
I am Satyanarayana from Srinidhi Engineering College, sir. Sir, backstepping algorithm, can we apply the integration of the storage devices and RES to the microgrid?
Yes, actually, the storage is also a component here that comes under the dynamics part of it. The same, because the controller has nothing to do with any storage or any VSI, any number of things. It doesn't affect much because we have taken 13 states. So if you put the storage somewhere in between, you have to choose another state there. So still the controller can be tailored into. So no more difficulty. You can use.
Then at what point we can improve, sir, if you use that one in storage
Which,
cases?
which one will improve?
What is the impact? Settling time reduces or THD reduces. What factor it will
No.
affect?
Storage. You see, the storage part is taking care of the stabilization of the grid. It has nothing to do with the THD. Storage doesn't contribute to THD. Okay.
This algorithm, sir. This algorithm,
No,
how
no.
it
This
affect?
algorithm will be the same efficient, but only thing that it will take care of the dimension of the state. Model will increase, and therefore the controller implementation will take little longer time. That's it.
Settling time will be reduced.
Say I cannot say that settling time may not be reduced also. The same it will remain or maybe little less or more, but there's nothing to settling time because when you put a storage, it is basically a stability aspect of it, not about the controller performance aspect.
Okay, thank you, sir.
So when you consider the dynamics of PV, renewable energy system, and the energy storage, is there any change that we have to consider?
Yeah, there will be change. Yeah, that's a good question. Actually, here we have simulated it. So when you change, let us say you are right. Let us say there is a 1 megawatt power plant. So 1 megawatt power plant might be a big power you listen, but that comes by small, PV cell connected in arrays and arrays connected into multiple loops and all that. So obviously, when you take a PV dynamics, the equation altogether will get changed because we have taken some DC source with inverter as a representation of a DG unit. But when you put the actual PV dynamics or a wind energy dynamics, obviously the dynamics will change.
Okay, thank you, sir.
As Professor Subudhi sir has some busy schedule, so if anyone has any question, you can send it email.
No, I am open. I have still 10 minutes time. If you are asking, I will be there. Next meeting, I can attend 10:15. No problem.
Yes, sir. Thank you, sir.
Good morning, sir.
I am Prashant from NIT Trichy.
Yes, please.
Sir, means this backstepping controller, is it meant for zeroth layer only, or we can use it in secondary and tertiary layer also?
This you see, this is a very interesting question, of course. Actually, we have nothing to do in the tertiary layer. No controller actually necessary there. This is only a operation research problem, what you call optimization problem in the tertiary layer. Tertiary layer doesn't involve much control. Actually, control more needed in the secondary layer because primary layer anyway we go for a what you call group control. Secondary layer only you put all these controllers, right?
So, sir, means one controller is needed at the terminal of each DG.
No. when you the option is yours. Either you can use all the digits together, one controller, that is a centralized controller.
No, sir, I'm talking about just this backstepping controller.
Backstepping controller here, yes, for each digit you need one controller. I. Yes, you are right. You are right.
G. And sir,
You are right.
what communication you used for DG to DG communication? Is what type of communication we can use here?
It is RS445 you have used.
G. Okay. Okay, sir. Okay. Thank you.
Sir, if we are doing simulation of this scenario, how relevant is the communication delay in that simulation purpose? Will it be that much significant to show that, or will it be that much visible enough, the communication delay in simulation work?
Yeah, so you see, this is a very good observation. Actually, communication delay is inherent. What happens, the communication delay provides, creates a latency problem, a packet dropout problem. That means your controller needs some sensor input. Now, if the sensor input doesn't reach in time, it reaches delay. So you have to do something for the control, because that time the state is not available. So therefore, they how to represent a time delay in our BTech, control. That means a state, let us say there is a transfer function model. We say the transfer function GS equal to K e to the power minus STD divided by 1 plus ST. It is a first order model with time delay. So that takes care of it. So the communication delay we represent in that model and then conclude it. Similar delay compensation techniques are there. Similarly, when you use a state variable model, you could notice that x minus tau I have written. That tau represents the communication delay. Now that communication delay is also taken care of by the controller. Okay.
Oh, okay.
Good morning, sir. One more question, sir.
Yeah.
So actually, my area is integrating a PV and storage systems to the DC microgrid, sir. So I'm focusing the settling time, sir. Is there any best algorithms to reduce the settling time as well as reduce the THD values?
Yeah. So you see, you have two different questions. One is to reduce the THD.
Yes, sir.
THD is basically dependent on the harmonics compensation.
Okay, sir.
So you have to integrate some active power filtering algorithm there along with the, so the same VSI will take a active power filtering algorithm that will fast, like I will tell you one thing, like there is a noise. So how to compensate the noise? So you have to provide an anti-noise, then that is cancelled.
Yes, sir.
Similarly, in case of active power filtering, what is done? The, harmonics is estimated. Okay. Then you have to compensate in the opposite, like the sound active power filter. So one is this, your first question is the THD compensation that needs a active power filtering control embedded with this control. Another control is needed here. And regarding the settling time, any controller, the settling time depends upon its characteristics, its performance. So you have to tune the gains or you have to integrate. So the settling time is basically, also related to your steady state error. So
Yes, sir.
maybe integral component you can add in that controller. Okay. So that will be helping you.
Is it help to the fuzzy logic ANFS, sir?
No, I don't have any idea. Fuzzy logic will do or neural network will do. I cannot answer that. But only thing I can say that you can try them. But nevertheless, if you choose a because these microgrids, etc., they are basically uncertain systems. So my opinion, fuzzy logic control is good in the uncertain system handling. You can still try that, and you can go for a fuzzy adaptive control if you wish. But neural network control, I will not advise because the implementation will take a lot of time.
Thank you, sir.
I would like to extend our heartfelt thanks to Professor Bidyadhar Subudhi sir for his amazing lectures and discussion. We truly appreciate you and your time for our institute. Thank you so much, sir.
Thank you.
Thank you very much, sir. In spite of busy schedule in your current assignment as a director of NIT Warangal, you have given us so much time to our participants. Thank you. Thank you very much, sir.
Thank you, Prabhat, for inviting me and getting a chance to talk to all these interesting young participants. We are in their middle of their research and wish them grand success to your course. Thank you very much.
Thank you, sir.
Thank you. Thank you, sir.
Thank you.
Our next session will be started at 11:30 a.m. by Professor Premlata Jena ma'am from IIT Roorkee.